3.4 is the properties of logarithmic functions. So we start out with our properties of logs, and it says for any positive number m, n, and b, where b is not equal to 1, and p is any real number, the following properties apply. So we have the product property that says if we're taking the log with any base of two things that are being multiplied, we can separate them by adding them. The quotient property says if we're taking the log of any base of two things that are being divided, we can separate them by subtraction. And it's always the numerator goes first, and then the denominator part will go second. And the power property says that if we have some log with any base of something that has an exponent, we can take that exponent and move it in front of its log. So it becomes the coefficient of that log. And so remember, this works for any base. So it could be base B, base 10, base E, base 7, base 5, any base, okay? All right, so let's practice this. So it tells us to expand the following logarithms using the properties. So notice on A that we have three things here that are being multiplied. And so we can separate them by addition. So we're going to have log of 8 plus log of x plus log of y to the fourth. Now, log of 8, if we try to work that out, it's not going to work for us, so we don't have to. But if it had been like log of 100, if we set that up as an exponential function, we would have been able to solve it, so we need to. Log of x, I can't do anything with, but this log of y to the fourth, we have that power property that tells us we can move that 4 in front of its log. So we're going to keep our log of 8 plus our log of x plus, and then we're going to move that 4 as a coefficient, so 4 times the log of y. B, notice, has division. So let's first separate it. If it's being divided, then we can subtract them. So we're going to take the natural log of the numerator minus the natural log of the denominator. Now, remember, taking the square root of something is the same as raising it to the 1/2. So that natural log of the square root of x squared plus 5 becomes the natural log of x squared plus 5 raised to the exponent, which is a 1, over the root, which was 2. And then I can't do anything with the rest of this, so I'm going to bring it down. And then now, because we have that power, we're going to remove it to become the coefficient. So we end up with 1/2 natural log of x squared plus 5 minus the natural log of x. Then we're going to do the opposite in example 2. We're going to condense it. So first thing we notice is we have two things being subtracted, but it's not just a log minus a log. Okay, it's a log minus 2 times a log. So we can't combine them until we do something with that 2. Now I'm going to separate the 2 and the negative, because if I move I'm going to move this, since it's a coefficient, I'll be able to move it as the exponent. If I take the negative with it, then I'm going to have a negative exponent. And we can do that, but y'all don't usually like negative exponents. So this is the natural log of x to the 5th minus the natural log of xy quantity squared. And then we have options here. I'm going to go ahead and give the square to both of these. So we get the natural log of x to the 5th minus the natural log of x squared y squared. And then we can go ahead and put it together because we got subtraction, which means we can put it together through division. So we're going to write the natural log. The first one, remember, is our numerator, minus, so divided by, and then our denominator is the second one. But on this one, we can still reduce what we're taking the natural log of there, because we have an x in the numerator and the denominator. So we're going to get the natural log of x to the 5th divided by x squared is x cubed, and we still have that y squared on bottom. B, all we have is a log minus a log. So we can go ahead and put that together. So we got log of the first one's our numerator over the second one that's our denominator. We can't do anything with that. So there is our answer. And C is more like A was. Notice we have a log plus a log, but we get coefficients in front of them. So we're going to need to take those coefficients and make them become the exponents. So we're going to get the natural log of x cubed y all to the third plus the natural log of yz squared all to the second. And then because there's no plus or minus signs in parentheses, I'm going to go ahead and give that cube to both of them. So we get the natural log of x to the ninth, y to the third, plus, I'm going to do the same thing on the second one here. So I get the natural log of y squared, z to the fourth. And then I can put them together because they're being added. We can combine them by multiplying. So we're going to have natural log of the first, so x to the ninth, y cubed, times the second, so y squared, z to the fourth. Remember, when variables are written side by side, that means they're all being multiplied, right? So therefore, I can combine my two that have like bases. So I'm going to get the natural log of x to the ninth, y to the fifth, and then our z to the fourth. And we can't do anything else with that, so that will be our solution. All right, and so we've looked at putting some of the logarithms into our calculator, but our calculator is base 10. So we can't, or base E if we use a natural log. So we cannot put like a log base 3 or log base 6 or anything like that in our calculator. So we have a change of base formula that will help us to be able to do so. Or we can change it to any base. So if we have this problem, let's say it's just log base B of x, we can change it to base A by saying we're going to take log base A of x over log base A of B. Or if I wanted to be able to put it in my calculator and use my log button, I could say it's log of x, because log base 10 of x over log base 10 of b. Or I could use natural log, so it would be natural log of x over the natural log of b. Just depends on what base we need. So on A, our example 3 here, it says evaluate the logs by changing the base. So it wants us to put these in our calculator. And so log base 3 of 13, I can write that as log of 13 over log of 3. The taller number is going to go to the top part, and the little base will always be the number that's on bottom, okay? So we're going to type this into our calculator. Log of 13. Now when you hit the log, remember it opens a parenthesis, so make sure you close it, okay? So log of 13 divided by log of 3, and we get approximately 2.335. Now, I wrote a little big there, but what if I instead wanted to use a natural log button on my calculator? I would just type in the natural log of 13 over the natural log of 3, hit enter, and it's going to give me the same exact answer. All right, so either way, 2.335 is a good approximation. All right, so on B, let's just use common logs. So to solve this one, so we're going to take log of the taller number over log of the base. And so we put this in our calculator, and we're going to get approximately 1.285. And let's do C, but let's use natural logs this time. So it's the same idea, the natural log of the taller number over the natural log of the base. I'm going to put this in my calculator, and it gives me -1, which means I could have worked out that log base 1/2 of 2 by doing that b to the y equals x, because we got a whole number answer. All right, so on this one, we've talked about this before. So remember what the graph of a logarithmic function looks like, a parent one. It has a vertical asymptote at x equals 0. And it's going to look something like this when it's graphed, and the parent one will go through the point 1, 0. So our domain is going to be 0, not included, to infinity. Our range keeps going up and keeps going down, so negative infinity to infinity. It is continuous, and it's increasing over the entire domain. Symmetry, it's not symmetric to the x or y. Well, we don't actually check the x-axis because otherwise it's not a function. It's not symmetric to the y-axis or the origin or the line y equals x, which also means it's not even or odd. Is it bounded above or below? Neither, because it keeps going up and down, so it's unbounded. Local extrema, there's no hilltops or valleys. Horizontal asymptote, there's no horizontal asymptote. Vertical asymptote at x equals 0. And then the end behavior. So we've done the end behavior, and we've done a lot of it just using the arrows. So think about this. Let's use arrows first, and then we're going to go ahead and we're going to change it to limit notation. Okay, so as x goes towards the left, as we go to the left, x isn't going to go past 0. So we're going to say as x goes towards 0, y, notice as we go to the left here, we're going down. So our y's are going to go to negative infinity. And so to write that as a limit, we would write limit as x approaches 0, f of x equals, and then we put that negative infinity. And then we can go to the right, so as x goes towards positive infinity, because as we go to the right, it's going to just keep going, so it's going to where x is positive infinity. Our y's are going to slowly keep going up, so they're also going to positive infinity. So to write that in limit notation, we'd say the limit as x approaches positive infinity, f of x equals, where our y is going to go to positive infinity. And so this is how we would write them both as a limit. We need to start practicing the limit notation instead of just with the arrows, okay? All right, so example 4 says describe how to transform the graph of f of x equals the natural log of x into the graph of the given function. So the natural log of x is going to be our parent function. So notice on A, though, it's not in natural log, so I'm going to have to change it to that. So we have log base 5 of x. Well, to change that to natural log, we know that's natural log of x over the natural log of 5. So we could say, okay, well, that's the same thing as saying the natural log of x over, and we can calculate that natural log of 5. And so we know the natural log of 5 is 1.609. Well, remember, dividing by a number is the same as multiplying by its reciprocal. So instead of saying we're dividing by 1.609, we could say we're multiplying by 1 over 1.609 times the natural log of x. And then 1 over 1.609 is approximately 0.621 times the natural log of x. And so we can use this equation now to tell us what that transformation is going to do. So that 0.621, it's not inside with x when it's vertical. It's being multiplied, so it's a stretch or compression. Since this one's smaller than 1, it's going to be a compression by the 0.621. Now, for our parent function, remember we've got the vertical asymptote, and we've got our graph here. What is a vertical compression going to do? If we push it from the top and the bottom, what will that do to our graph? Well, as we push from the top, it's going to squish it down more. And as we push it from the bottom, it's going to squish it, don't go past that asymptote there. It's going to squish it up some. And so that would be what our graph will look like. All right, so for B, we're going to do the same thing. So for B, we got log base 1/2 of x. And we need to change that into a natural log. So it's a natural log of x over the natural log of 1/2. So that's the natural log of x over the natural log of 1/2 is negative 0.693. which means dividing by that number is the same as multiplying by the reciprocal. So it's 1 over negative 0.693 natural log of x, which is approximately negative 1.44 natural log of x. So we have that negative, which means we're going to reflect across the x-axis. And that 1.44 is being multiplied. It's not in with x, so we know it's a vertical. It's being multiplied, so it's a stretch or compression. And it's greater than 0, because remember the negative we don't look at because it was a reflection. The number is greater than 0, so it means it's going to be a stretch by 1.44. All right, so our parent function has a vertical asymptote at x equals 0. It's going to be coming up looking like this. Now, be careful on this one. I'm going to kind of do it in 2 steps here. So the first thing is it's going to reflect across the x-axis. So it's going to look like this, okay? But then it's being vertically stretched. So as I pull it down, it's going to flatten out, come more straight down, and the same thing going up. So our graph is going to look more straighter than what it was. It's not straight up and down, but it's going to look straighter than what it was. All right, and then example 5. It says the data below represents the price and quantity demand for a personal computer. Use a graphing utility to draw the scatter plot. It wants us to find the log function of the data. So for this one, we're going to use our stat edit. So we're going to stat. Number 1 is edit. And we're going to list these numbers in L1 and L2. Once we do that, we're going to go back to stat. We're going to go over to calc. And we want a log function. So you're going to go look for the one. There's not one that says log, okay? Logistic is different than log. It's going to say the only one we have with the log is the ln regression, okay? So choose it. And then calculate it. And so it should tell you the y equals a times, no, I'm sorry, wrong thing. Should tell you a minus b natural log of x. It's going to tell you like a is 569.754. B is 53.907. And then just plug them in. So your equation should be y equals 569.754. I'm sorry, this was a negative. That was a plus. I apologize. So minus 53.907. So there's our equation. Oh, I forgot the log of x. Natural log of x. Well, natural log of x. Let's do that. All right, B says use a function above to find the number of personal computers that would be demanded if the price was $1,500. Price is $1,500. That was my L1. Those are my x's. So we're just going to plug in that x equals 1,500. So y equals this number, or this equation. And I'm going to plug in 1,500 for my x. And then we should get approximately 176 computers.